Okay, so the last three classes we looked at some secrets of life. I mean, some basics of molecular biology. I think that much was enough for you to understand many things. In fact, now I will be covering after some time, the synthesis mechanism, how it happens, and the sequencing mechanism. How do we do sequencing and synthesis of the DNA? That will require some chemistry also, but we will cover that later on. Uh, now, in terms of codecs, I have already covered some of the basic ones, you know, and now today I'm going to talk about DNA fountain code, which was a paper in 2017. It's a really beautiful paper. Now you will see that here uh, the authors have modeled the DNA storage channel by combining some of the basic ideas from information theory. So you are familiar with binary symmetric channel. If you remember, I talked about it, right? 0 can go to 1, 1 go to 0 with probability P, right? And 0 can go to 0 and 1 can go to 1 with 1 minus P, right? And I also briefly discussed about the constraint channel, right? So if you want to revisit any of these concepts, of course, there is a one famous book, Elements of Information Theory, which assumes certain things. But apart from that, there is a one very beautiful book by David Mackay. David Mackay, although he is no more in this world now, but he has written a very nice book, and I think I can show you that book. You can look at it for any thing that you require from the information theory point of view. It's a beautiful book. You can see that this book is available. As a PDF also, you can look at it, right? So this is his website. This is a really good book. You can find different kind of channels. So some of you have already, those who have done the course on digital communication, right? Have you done the course on digital communication? Very good. So you know some of the stuff. Uh, Obviously, so I'm assuming some of the probability stuff here as well, right? And some concept like entropy and so on. I think you know how to compute entropy and so on of a random variable, right? Those things are there. So anyway, so please do look at this book. You can download it, and I think you can read it online free of cost. But if you want, you can buy, say, maybe around $50 or something. The book is available. In fact, if you want, there are 16 lectures by David Mackay itself on this, right? So which you can look at it. It's some interesting work. Uh, Unfortunately, he's no more with us. He died some time ago. So, okay. So with those assumptions in mind, now you see that there is an issue. Whenever we want to model, so one way say that, okay, there are different kind of errors that are happening. You have already seen because of homopolymer, right? Repetition of bits more than 3 nucleotides creates a problem in terms of deletion will happen and so on. There could be bit flip, there could be insertion, deletion of letters, ACGT, right? So this paper I like because, of course, there are many more way you can model the things. So first, I will look at the DNA storage model that they have proposed by combining constraint channel and the eraser channel together. Okay, so I'm going to describe that briefly, and certain assumptions that are there, right? And now the good thing is that whatever work was done previously before them, they have shown that how to calculate using the formulas that they have come up with, right? You can how to calculate different parameters of the model, right? So it's something really interesting paper. So, you will find that there are some other variations. So basically what happens, people will modify the error model a little bit. Okay, and you get a different kind of, so you can look at a different channel. For example, there is a DNA shuffling channel. Somebody has studied, right? Different kind of literature is there. But I think rather than going into all of them, I'm going to focus on two codecs. One is Fountain Codec, another one is Yin-Yang Codec, which was done by George Church Group this year only. So these two are important ones which we are covering. Okay, and then after that we will be covering variations in terms of what mathematical model they have considered and what are the main results towards the end. So basically, we are dividing the whole literature into three parts. Elementary part, which we have already covered about the codecs. Second part, I'm going to do these two important codecs, which are DNA Fountain Codec and Yin-Yang Codec. And third part, rest of the stuff, which is slight variations. So basically what happens, there are some group of authors, they will slightly modify the model, right? And they keep on writing papers, series of papers on that, right? And then there are some other group of models, they will modify the channel and do a couple of other things, right? So this is really interesting. So first I will talk about the model. Then I will talk about briefly about the fountain codes, because fountain codes are very, very important. So Michael Luby and, Amin Shukrelahi, these are the people who have done a lot of work in this area. So there are codes like Tornado codes, Raptor codes, LT codes. These are very, very popular. So fountain codes means there is a stream of bits is coming, and how do you model it, right? I mean, in terms of things. So I'll describe that fountain codes. These are quite beautiful codes. Okay. And then I will say that what is the DNA fountain code. So I think at least 2 lectures, maybe 2 to 3 lectures will be required to cover all the stuff what we are going to do it here. So let me look at the model first. Okay. So basically, now I'm going to look at this paper. Okay. 2017. So here it must be given somewhere. Yeah, this one. Sorry, that is not the one. This one. We are looking at this paper, number 8. Appeared in Science. Okay. So Ehrlich and Zielinski, DNA fountain code. So you will see that if you go to their link given in the paper, you can find the implementation of the codec as well. So you can actually see, all the things. Okay, so let me, in this channel, first of all, what kind of errors are possible? So errors are happening because of what kind of things happening in the channel? DNA synthesis, imperfection. That is one reason. Then PCR dropout. So they have considered PCR dropout as well. So I think from the last lecture, you know what is PCR, polymerase chain reaction, right? PCR dropout happens, so they are modeled as a eraser channel. Then we have stutter noise. We also have degradation. Of DNA molecules over time. That's another reason. And then sequencing errors. So these are the errors. And apart from this, you can get sequencing and synthesis error because of 2 more constraints. One is homopolymer runs. Runs means stretch of, CCCC or AAA or TTTT or GGG like that, right? Plus GC content. These two things will give rise to synthesis and sequencing errors, right? So we are assuming errors coming from these things. So 1, 2, 3, 4, 5, right? 1, 2, 3, 5, yeah. Okay. And so basically, if we control these kind of things, we will reduce synthesis and sequencing error. Okay. And apart from that, so now I think there are certain experimental observations. So I am referring to them. There is a work by Rods et al. In 2012. So they have observed that oligos, the strands of DNA, ACGT is called as oligos with GC content more than 60% exhibits higher dropout rate. Okay. And most PCR error, polymerase chain reaction errors, occur in GC rich region. Okay. So this is the observation. So ideal is that the GC content should be around 50%. Okay. Second observation by Ross, 2013. So if homopolymer run is more than 4 nucleotides, the insertion deletion rates starts climbing. Okay, so I think I can show you a picture here. Maybe you see here is the error rates of Illumina sequencing. Illumina, so in Illumina sequencing, I'll talk about different kind of sequencing. So error rates of this sequencing as a function of GC content and homopolymer length. So you can see that this is the with respect to homopolymer and with respect to GC content, right? So light blue here graph shows the mismatches. Okay, dark blue shows the deletions and purple shows the insertions. Okay, so taken this picture again from this paper itself, DNA fountain nibbles. I think this paper you must read, compulsory for everyone, So you observe that. So if homopolymer length is more than 4, you see, okay, so there is a problem. Then we have also Ananda et al. Observed in 2013 that PCR slippage errors. So if homopolymer is more than 4 base pair. Okay, so these are basically certain common observations. Okay. So because of these observations in the model, what we are going to do, we divide oligos into two classes. Valid and invalid. What do you mean by valid classes? When GC content is within 0.5 plus minus CGC. CGC is a parameter, okay? And second, length, or I would say largest homopolymer length is up to M nucleotides. Okay, so these are the two observations. I mean, these are so two classifications. We will call a DNA oligo. Oligo means a strand of DNA as valid if GC content is within this range, 0.5 plus minus CGC. So this is a parameter we can, can control so that is the desirable range. And the largest homopolymer length is up to M nucleotides, right? If these two things are satisfied, then we call it as a valid DNA oligo. So you want these things in the DNA strand. Otherwise, it is invalid. Okay. So these two classifications we can do. Okay. Valid or invalid oligos. Now, I can define the coding potential B. The coding potential B is entropy of each nucleotide in valid sequence. Okay. So I will show you how to compute this coding potential. Okay, but there are a couple of other parameters that we need to see before. So entropy of each nucleotide in valid sequence. Okay. So valid sequences are exposed to a low delta V dropout rate. So this is additional constraint. All these valid sequences are exposed to low dropout rate delta V. So now you see that because of PCR, we are having this condition, right? The PCR will have the dropout. Now the length of total oligo is L. L nucleotides. And you see that in most of the architectures, because these nucleotides, we are storing data in the nucleotides and they are in a mixed pool. So whenever we are storing data, we should have some sort of indexing with each nucleotide. So indexing, we need to reserve certain nucleotides for indexing, right? So I'm saying that there are, I'll call it as a fraction of nucleotides for indexing is I. Okay. I nucleotides are reserved for indexing and L is the total oligo size. And also K is the number of segments needed for decoding the input file. So basically, there are parameters like M, CGC, I, and delta V. These four parameters. What is M? Anyone from the audience? What is M? What is M? You can see that largest homopolymer length up to M nucleotides. So size of the homopolymer that is allowed is M nucleotide in a DNA strand, right? M is that parameter. CGC is the parameter to control the GC content. Okay? If you remember from here. So 0.5 plus minus GC. Okay? I is the length of the index. How many nucleotides are used for indexing? And delta V is the dropout rate, right? So these four parameters of the model are basically can be used to approximate the information capacity. So total capacity, how much capacity? So basically, you see, when we are computing whenever we are coming with any scheme, we need to define the architecture of the chunk, right? So when we have the chunk, some indexing file, some other thing, all the chunk architecture is very, very important. Okay. So now, based on these chunk architectures, we can come up with the information density. Okay. So now I'll try to give a formula. So basically, see, I mean, this is something that I should say that here, again, it will be a difficulty problem, but at least you can look at it. So here we have assumed that, the homopolymers of length M we are considering, right? So now, rather than homopolymer means single bit, you can look at the conflict-free strings that and the model will be a little bit generalized. So you can actually compute the formula for, that has not been done anywhere. Nobody has done that, right? This is something, a problem which one can look at it, right? So here we are allowing homopolymer, a single bit. But if you do generalize it, blocks repetition, if you avoid of certain size, right? What will be the formula you can compute? So that is it. So I am going to do it for this, but maybe you can compute it for the other thing. Okay. So now I think if you look at, I have a table here. So these parameters, M, the maximum homopolymer length, 3 nucleotides. So remember I mentioned earlier also 3 nucleotides is okay. More than 3 is creating a problem, right? But anyway, in the model we have to take some general number, right? So that you can actually calculate the formula, right? CGC is the maximal deviation of GC content from 0.5. How much differing, right? That parameter. Okay. And B is the coding potential. Actually, for this scheme, it turns out to be 1.98. I'll show you how to calculate that, right? So I is the index overhead, right? Index overhead. How many nucleotides are used for the indexing? L is the oligo length, so 100 to 200 nucleotides, and delta V is the dropout rates between possible values 0 to 0.005. Okay, so basically these parameters will help you to analyze the model, right? So people who are developing, I mean, if you want to develop a error analysis thing, right? So if you write a software, you can choose these parameters and see what happens. You can introduce the drop rates of different variables and see the performance of the codec, right? You can come up with the performance for the codec. Okay. Okay. So now I can describe what is the channel actually. But before that, I would like to, so I'm going to do the now quantitative analysis. First of all, I will just recall what is BEC, binary eraser channel. I'm just recalling it here. So we have 1 and 1. So we are sending 1. suppose there is a probability of erasing the bit is PE. So you receive this side is X, this side is Y, right? So probability of erasing is PE. So probability of correctly receiving is 1 minus PE. If 1 is sent, right? And probability of erasing is PE, and correctly received is 1 minus PE. Similarly, if there is a 0 and I sent it, probability of erasing is PE, getting correct is 1 minus PE. PE is your erasal probability. Okay? Have you studied this in your course, right? Somewhere in digital communication? Procus, maybe? Which book? Procus? Okay. So eraser channel is important. Now, actually, you might have. So basically, X is a transmitted random variable with alphabet 0, 1, and Y is the received variable with alphabet 0, 1, and E. Eraser symbol, right? So I can compute this probability that Y is equal to 0 and X equal to 0. What is this probability? X is transmitted, 0 is transmitted and 0 is received. What is the probability? 1 minus PE, right? From the channel itself, you can observe that. Fine. What is the probability for Y is equal to 0 and X is equal to 1? This is interesting. Tell me, do you know? So flipping is not all right. So this probability is 0 actually. Okay. Probability of Y is 1 and X is 0 is 0. Probability of Y is equal to 1, X equal to 1, 1 minus PE. Probability of Y is erased when 0 is sent is PE, and probability of Y is erased. When 1 is erased, basically the probability is PE. And also, it is known that channel capacity of a binary eraser channel 1 minus PE. Right? And this is attained with a uniform distribution. For X. Means when half of the input should be 0 and half of the input should be 1, then this capacity is achieved. By the way, for the deletion channel, the formula for capacity is still an open problem. So some of you can use as a T problem, right? So you may require more, right? So you have to use your skills of probability and statistics, right? To do some analysis and and information theory. For deletion channel, that there is no formula yet, so one can try to find out. Deletion is very important here, right? We can go for the single deletion or whatever, right? So take the deletion channel. So as an exercise, I would like to invite you, see what is deletion channel and, how we can say what will happen to the capacity. Think about it at least, maybe you can get some idea. Okay. So okay, so now here is the DNA storage channel that these people are considering. There are two parts. So of course, transmitter is transmitting. So synthesis of DNA oligos, which is having message plus index of length I nucleotides, right? Message plus I nucleotides. That is what you are transmitting. Constraint channel, what it is doing? So basically, homopolymers up to M nucleotides and GC content is within 0.5 plus minus GC, right? These two conditions, which we assume is already there, right? So coding potential is B bits per nucleotide. Now you see that, I mean, you know that, I mean, if you don't do any error correction, so 2 nucleotides is the maximum that is possible per, right? 2 bits per nucleotide is possible, right? That is the kind of thing that you can do anyway. Now, eraser channel, so we have a PCR and sequencing dropouts with rate delta V, right? So polymerase chain reaction is modeled as a eraser channel, okay? Certain things are erased. And as I mentioned that this is observed more when there is a rich GC content, more than 60%, then there is a problem. This rate will be more actually, right? So this is how they model. And then the receiver. Receiver means sequencing, means reading the DNA oligos. This is the entire channel that they considered. Okay. Now, again, there is a scope for research. Here, you can modify constraints seen as there, right? Come up with a new model. If you come up with a new model, analyze it, simulate it, then come up with a coding scheme, and then do the experiment. It's a beautiful paper, right? Can come if you can achieve the capacity. Anyway, again, this I have taken it from this same paper. In the 4 pages, 4 beautiful pages, I would say, everything is summarized in this paper. Okay. Now, in order to compute the coding potential, I have to now assume, I mean, I have to use certain notations, which I am going to use now. Okay. First, AX is set of all possible transmitted DNA sequences of length L nucleotides. So L is the total oligo length, right, which we are transmitting. Note that I nucleotides out of this is for indexing. Okay. Similarly, we have AY. So basically, set of all received sequences. Okay. So we have AX, AY, our whole space. X is a random DNA sequence from AX, and Y random DNA sequence from AY. Okay. So 4 notations I'm using. AX, set of all possible transmitted DNA sequences of length L nucleotides. AY, set of all possible received sequences. And X and Y are the corresponding random DNA sequences, right? Fine. Now, again, assuming you know information theory, the mutual information of X and Y is HX minus HX conditioned Y. What is HX? Anyone? Entropy. Fine. So entropy in bits of X. This is entropy. And I think you know the formula for calculating the entropy, right? Fine. So HXY is conditional entropy of X given Y. Now the information capacity of each oligo is defined as is defined as C stand for maximum Px mutual of Ix. This is the standard formula, right? So this is for each oligo of length L. Similarly, the information capacity per nucleotide is CNT C divided by L, because the total size is L, right? Okay. Now actually I'm going to use a result which is there in constraint channel. Okay. This result is given, I think, at page number, if you want to see, I think it is, yeah, page number 252, 251 at the David Mackey book, which I have showed to you, right? There, this is given. So I'm just using that result because assuming that this is known, right? For the constraint channel, the mutual information is maximized by eq probable transmission of only valid sequences. Refer to okay, page 250 to 251 or something. So for constraint channel, the mutual information is maximized by probable transmission of only valid sequences. So that means, you know, can say that property of X is where this bar denotes the size of AX. Okay. Now, valid sequences are perfectly received with a probability 1 minus delta V, and valid sequences dropped out with probability delta V. This is actually from the PCR region, right? The second portion of the channel, right? We have the dropout rate of delta V, right? So for that channel, so for researchers, so valid sequences are coming from this side where the homopolymer and the other constraint is there. Now we go to the PCR region, right? So we have the valid sequences perfectly, received with a probability 1 minus delta V and dropped out with probability delta V. That is the, eraser channel, right? So this will give rise to that the mutual information X raised to Y is 0, and this will give us that the mutual information X, so sorry, not mutual, the conditional probability is here Hx, here it is 0. This implies that overall conditional probability I can compute. This will be delta V times H of X. Okay. Therefore, I can compute the capacity of each nucleotide is C and T is equal to Hx minus Hx condition Y divided by L. I know the value from the top. H, this is delta V times Hx divided by L. This is equal to 1 minus delta V times Hx divided by L. Now this is nothing but 1 minus delta V. Hx is nothing but log 2 base AX we just saw divided by L. Right? Entropy of X, as you see, is this here. I'm just substituting it. So capacity per nucleotide turns out to be 1 minus delta V log 2 base size of AX. So valid sequences. What is delta V? Is the dropout rate, right, of the channel. So I think I will stop at this point because then I have to do some more calculations. I don't want to because I don't have enough time, I guess, to finish that. Anyway, so I think so next time I am going to cover simplifications of this formula, right? Again, certain assumptions, and then I will show you how to calculate, you know, this formula for all the schemes. So you can actually compute the coding potential for each of the schemes, you know, which are there. So this is a very simple model I am considering. Of course, there are, as I mentioned, there are different kind of models having considered, but this is reasonably good enough to do various things, right? It is good with respect to physical density. It is good with respect to information density. So this model is really good, right? So I think that's all. So now I will simplify this quantity here further the next class. So I hope by the time you can also read and you know, if you want the paper I have posted in the folder, then we can come and tomorrow we can discuss it further, right? गर्भा के कारण थके हुए लग रहा तुम? Okay. Okay, thank you.